Hi, I'm Chris Brown, and this is the fourth module in a series on Introduction to Axiomatic Design. It's part of a course offered here at WPI on axiomatic design of manufacturing processes. I am a professor of mechanical engineering, and so for the next 20 minutes or so, we are going to be looking at how to represent designs essentially symbolically. So we need some way of representing design symbolically so that we can apply the axioms for axiomatic design, and so that we can improve design by manipulating the symbols. So the application of the axioms, as we've been discussing, provides us with a kind of functional modeling so that we can tell which design solutions, or which potential design solutions, are the most promising or will be the best early in the design process, so we can allocate resources appropriately. We also want to be able to capture the design symbolically so that we can improve communications about the design solution, and this will speed up the design process. So how do we apply the axioms? Well, how are Newton's laws applied? We can use this as a parallel. So Newton's laws, in order to apply these, we often go and use free body diagrams for Newtonian mechanics. And so what we do when we do that is we decompose the problem into solvable elements. So the free body diagrams have coordinate systems, and we know the orientations between the coordinate systems. And we can see what the forces are and the motion is in any coordinate system that we choose, once we've decomposed it properly. And this gives us a kind of solvable element, and this provides some structure so that we can apply Newton's laws. So what's the equivalent of a free body diagram for looking at a design? And how do we decompose design solutions to get them into this kind of fx, fy, fz sort of formulation that is so enabling as we go to solve mechanics problems? So what's the structure of a design solution? How is that going to work? Now, we'll note as we go through this, there are some similarities actually between the structure of a decomposition to simplify mechanics problems and what we use in design. And there's a kind of naturalness of this as well. One of our decomposition, say, themes is going to be domains. And let's see how we can develop this. So you have here an image that I've taken off the web. And so we could ask the question, what is this? And obviously it's a bottle, and it's a plastic bottle. So how many different ways are there to describe it besides calling it a bottle? So try to think of some diverse ways of describing it. And maybe take a moment, even stop the video, and write down several brief, say less than 5-word descriptions that describe this thing on the right side of the screen. So describing design solutions. So first, the design solution needs to be described in words. The words are going to be easier to manipulate and communicate the design more easily. Now, as engineers, we're used to working more with numbers, and the numbers will come later. So we need to describe what we're doing, and there are two ways to look at the design. One is in the domains or spaces kind of direction, and these are categories of description that go from the customer to the manufacturer. And we represent these usually horizontally, although so that lots of times this is called the horizontal, I call it the horizontal decomposition into domains. Then there's a hierarchy of detail or of abstraction, we could say, and it goes from general to specific. And this we often represent vertically. And so this would be the vertical decomposition into a hierarchy of abstraction. So let's take a look at the design domains. The first design domain or space is the customer. And the elements of the customer domain are the CNs, or the customer needs. This is what adds value, and as we'll mention later, is the start of the value chain to show why it's worth doing all of the other things. The next design domain that we'll consider then is the functional domain. Now the elements of the functional domain are the FRs, or the functional requirements. Now you want to become conversant with these abbreviations. So you'll need to memorize CNs and FRs because we'll be using those over and over again. In the functional requirements of the FRs describe what the design does. The next domain we consider, and these sort of build on each other, is the physical domain. The elements of the physical domain are the design parameters, or DPs. And this describes what it looks like. And the final domain that we will be interested in, particularly in this course, is the process domain. And these are the PVs, or the process variables. And this describes how it is made. Now don't get hung up on the names. There are some people that say, oh no, we can't have the functional requirements there. These aren't really functional requirements. This describes what it does, and it comes from the customer needs. You could really call it anything you want. And in some ways it's unfortunate that the elements of the physical domain are known of as the design parameters, when the whole thing is the design and what are the parameters we're using for design. Doesn't matter. This describes what it looks like. And so the process variables could also be talking about machine tools or manufacturing systems that are going to be used to generate something. So don't get hung up on the names. Look at what they do. All right. So now that we've seen what these domains are, take a look at what you wrote down to describe the bottle, and see if the descriptions fit into some of the domains. Now, usually when I do this in class, we are able to come up with descriptions, the students do, and just ask to describe something, that can fit into the different domains. Now, the customer need is to have something to drink handy. So, it's like a beverage container. The functional requirement might be hold liquids for transport or travel. And the physical domain, it looks like a closable, watertight container. And in the process domain, well, it's blow molded plastic. So if you're describing how it's made, that goes in the process domain. And those are PVs, although I forgot to note it on the slide. The physical domain is the DPs, that things like dimensions, thickness, materials, things that would go on a print. And the FRs are what sort of functions does it fulfill. Keeps things from spilling, has an openable quality, but basically hold drinkable liquids maybe for travel. And then you could decompose that, as we'll see later, logically. All right, so see how you did there. Let's take a look at these domains now in a little bit more detail and see what they really mean. The customer domain is what adds value. This is what somebody's willing to pay for. And so this is the beginning of the value chain. Captures what the customer wants. Often, usually in non-engineering terms, may come from the marketing department. For example, can't be too slippery might be a customer need, a CN. Usually these customer needs relate to the highest level of the FRs, but they could contain many kinds of things at many levels. Constraints, for example, often show up in the customer domain, and and they may apply to other domains besides the functional domain. For example, lots of defense contracts have to be manufactured, or things for the Defense Department need to be manufactured in the United States. If it's going to be used around food or people, or you may want to avoid toxic substances. There's also legal constraints, and then constraints on cost, time, weight. So the customer needs need to be sorted through to see to which things they apply. Now, sometimes in a contract to produce something, there may in fact be thousands of customer needs expressed, particularly for some kinds of government work. And so these need to be sorted through to see what kind of things they are, and which domains they fit into, and if they are very general or specific. But generally you don't have so many of those things. All right. Functional domain, FR, is what it does. Now these are the next step in the value chain, and they translate the customer needs essentially into engineering terms. So they need to satisfy the customer needs, but they also need to give engineering something that engineering can work with. So the customer needs we think of as coming from marketing, and then now we start with the engineering design problem. So the FRs, they establish the design intent. Here's what it is intended to do. Here's the function that it is intended to fulfill. Now it's just the function. So this is the beginning of the desired solution, and we have to be careful, as we'll see, not to jump the gun on the solution. So it begins with a verb, all right, because it's describing a function. It's stated in the imperative, a command, like provide adequate friction. So the imperative is a command. And there's at least a verb, as in provide, and a noun, as in friction. And then it might be enough just to say provide friction, and then we can define in a note or something what adequate means, but often it helps to communicate, to know that we need to provide just a certain amount. So this could satisfy the customer need, can't be too slippery. All right, physical domain, DP, is what it looks like. Now these need to fulfill the FRs. So this is the next step on the value chain. So each DP should be selected to fulfill one FR. So we can remember from our example about the Monitor and the Virginia, the Virginia had a rudder that was trying to control the direction of fire and control the direction of the ship. And the Virginia had no way of doing those two things independently because it had one DP that was trying to fulfill two FRs. So, as we look in the physical domain, we should be looking for one DP for each FR. And ideally, the FR that it's chosen to fulfill would be the only one that it influences, although this is not always possible. But this would be the best situation. Okay. So in a mechanical design, and eventually the design parameters end up in some sort of CAD file or CAD drawing. These could be parts and features on parts, maybe nuts and bolts, or surface roughness at the most detailed level. Now, if I'm designing a machine, the nuts and bolts might be the most detailed level. But if I'm designing the nuts and bolts, that's starting off the most general level, and then I have to do the decomposition of that. And so it depends on what it is we're designing when we think the solution is obvious. So we'll be taking a look at the decomposition in the next lecture and defining a little bit more what it means to get to the most detailed level. So to follow up our example where the customer needs is that something's not too slippery, then it needs a rough surface. This is a design parameter that can provide adequate friction, which was the functional requirement. So CN is it's not too slippery, FR adequate friction, DP rough surface. Now, if we were designing, say, software instead of a physical part, we would be looking at routines or subroutines, and lines of code would be the most detailed level, perhaps. All right, what about the process domain, PVs, how you make it? So this is how we manufacture something and how we produce the elements that we find or we need in the physical domain. So, for example, it could be tooling, it could be process parameters. There should be a comma there, excuse me, between tooling and process parameters. If I'm processing different kinds of materials, the temperature can be very important, and I can change properties like hardness with the temperature and control of the temperature, or force, or some sort of displacement if we're looking at mechanical elements. So if we continue with our example on the friction, the FR in the friction example, that's going to be some sort of roughness in the physical domain. And then in the process domain, it could be the feed per pass in machining. If we take a larger feed per pass, the surface is rougher and then might provide better friction. That would be one way of doing it. So anyway, so there's an example, and the establishment of the value chain and the continuation of it. The customer wants something that's not too slippery. Here's an FR, here's a DP, and here's a PV, all linked through to the customer need. Now, let's consider the FRs. The FRs are special because, remember, the design is here to fulfill a function. So the FRs are important because that's the beginning of the engineering part of the design. And there's a special burden. No design can be better than its FRs. So when we specify an FR, say to have a certain friction coefficient, that's what it's going to have if we're successful. That's what we're shooting for. Did we want a greater friction coefficient? Well, if so, we should have asked for it. Is it not friction that we wanted? Maybe if it's not slippery, maybe it needs to be sticky. And then we should have had a different kind of description of the function. So the design is only going to be good as its FRs. Now the FRs also are defining the criteria for success. So we're going to see if we succeeded in design if we can fulfill the FRs. So these provide the desired function. So the FRs are what needs to be independently adjustable. Remember, the key thing, one of the key things is that maintain the independence of the functional requirements. So the FRs must be adjustable independently so we can adapt to change. And they have to be capable of providing that kind of change. So this is what makes it adjustable and controllable. So design is about solving problems, and this means changing something. If nothing had to change, there was no problem. So here's a representation, another representation of the domains: customer, functional, physical, and process. And inside the domains, we're showing a little bit more about the vertical hierarchies in the decomposition from general to specific. Now, as we go to generate these, and that'll be the subject of the next, one of the next modules, we use a sort of zigzagging decomposition, which is shown here, where we start with the function, then find the physical thing that is going to fulfill that, and then go to the next function and find the physical thing that will fulfill that as well. Now, one of the things that this is showing that we didn't show in the previous diagram is the constraints in the lower left. Now, the constraints, C's or cons, sometimes they're called. These are things that are not decouplable, essentially, and don't require physical DPs. And we'll talk more about constraints in a later module. But for right now, keep track of what the constraints are. These are things generally that it shouldn't do. They generally have limits, and they can influence all of the different domains. in addition, and I'm not emphasizing it in this, but the relationship between the physical and the process domain can be very similar to the relationship between the functional and the physical domain. And in a later module, we'll concentrate on how to develop the process domain. It's key to this course, and it's an interesting current issue in the development of axiomatic design. All right, we talk about different branches in axiomatic design, and as we do this decomposition from general to specific, you can see at the top we have the 0 level, the FR level, and then we have FR1, so, and a corresponding DP1, and what we call the children now, FR 1.1, 1.2, and 1.3, and a similar structure, parallel structure, in the physical space, because we need a physical element for each functional element. So these, in terms of the structure, will be mirrors. Of course, in terms of the description, they'll be different. So a branch starts with an upper level FR or DP, and then follows its way through the decomposition. And there's the second branch, and then the third branch. So we have, in this case, FR1 and its children, FR2 and its children, FR3 and its children, and the same thing in the DP, or the physical space. Now, we also talk about different levels, and this is in the hierarchy. So level 0 is FR0 and DP0, and there's only one, there are no children at the 0 level. In other words, we don't have 0.1 and 0.2. These are the overall objectives or overall function of the design, and the most general description of what it's going to be physically. These are immediately decomposed to FR1, 2, and 3 as we see here, and that would be level 1. And that's the highest level below the 0 level. And then there's level 3, which I have misnumbered there. That should be level 2, and those would be the children of level 1. So level 0, level 1, level 2 indicated here. So the lowest level, when you get to it, whatever that is often called the leaf level. So constraints, we talked about these a little bit previously. They can influence elements in any of the domains. They do not require DPs. They can influence several FRs. And for example, the bottle might be constrained to be made out of recyclable material and maybe some sort of shock-resistant material so it doesn't break when you drop it. Now here's an example, and we'll go into this in a little bit more detail in one of the next lectures. But this is just an example to show decomposition. This is done in Claro software, which is available at axiomaticdesign.com. And it's useful for doing these decompositions, and I recommend it highly. So this is for a jig grinder, and what we show is the 0 level and then the first level. And then to show sort of how we can further decompose it, here's a further decomposition of FR7 into 7.1, 7.2, 7.3, 7.4, 7.5, and then subsequent decompositions of each of these. Now, when we're looking at very large systems, we might actually have thousands of FR DP pairs if we're looking at more elaborate kinds of designs, say for a car. All right, so there's just an example of the decomposition. Now here's something else in the design description. So here is a solid model rendered in CAD. And so at this point the physical integration has been done, as all the different components have been put together. Now the important thing here, we note all these little numbers and arrows on here. Now these are to indicate what FR-DP pair this is referring to. So the DP is the physical elements that are already on there, but we need to know which FR is this referring to, so that we can understand the design intent. Otherwise, the beginning of the design review is somebody saying, well, what is this feature for? And somebody saying, well, that's for this. And what is this feature for? And there's no good systematic way of seeing all of that in all the different levels of detail. So this is a good way to represent the product or the design solution, the solid model with the different numbers that indicate which family or which branch and which level it came from. So horizontal decomposition goes into domains, the CN, that's what adds value, the FR, what it does, and the physical, what it looks like, and the process variable, how you make it. Then we have the constraints, what needs to be avoided. Now most of the time we're going to be looking at just the functional and physical parts. And we'll devote a special module or two to the manufacturing issues and how to look at those. Those can also be, even though we're going from physical to process, or process back to physical, the manufacturing can also be designed this way. So, and most of the literature on axiomatic design deals with FRs and DPs in this way. But for manufacturing processes, this of course is important, and we will look at that in some detail later. So what we're looking for in that is how do we adjust the DPs to get the DPs and tolerance. So very quickly, CNs and FRs. Customer needs. Establish the value and develop the functional requirements, the constraints, and a good formulation of FRs is critical for the design. The FRs communicate the objective and the intent. It defines the problem to be solved, and they're the foundation for the solution, a good statement of FRs. So the correct formulation of the FRs is one of the most important aspects in design. Let's note a couple things. Students often call the decomposition, or decomp, as sometimes we refer to it as when it's being used as a noun, the axiomatic design. This is not necessarily correct. Decomps can be developed and applied for other kinds of problems and other kinds of designs, and will have nothing to do with axiomatic design if the axioms haven't been followed. So the key part of the axiomatic design is, not surprisingly, the axioms. So literally the design is axiomatic only if it complies with the axioms, which it may if the decomp has been developed according to the procedures that we'll be talking about in the following lectures, where we're systematically maintaining the functional requirements. So where do we go from here? We need to see how to build the decomposition, and so we need to know something about this process. We need to learn how to apply the axioms and develop design and process matrices for manipulation. Thank you very much for your attention.